Chassis 16 posters. If anybody wants one, you're welcome to take it. I'm just going to throw them out.
What does it look like?
That's the right question.
You don't want one before the white hat. Huh?
Yeah. You. So can you hear me? Is this okay? Okay, so before I start, let me just mention that, well, I had heard from lots of students questions about whether there are any kind of nice canonical references for scattering amplitudes. I think it's good that there's some interest. There's one reference that I really highly recommend, which is actually a book that I think some of you may be familiar with, which is just called Scattering Amplitudes. What's, oh yeah, we use a different metric convention. That's okay. It's by Elvang and Huang. It's really a phenomenal overview of kind of starting from the very bottom all the way to the most interesting cutting edge stuff in amplitudes. I think if you have no interest in amplitudes at all, you should still look at it and read it just for culture, because I think most people think they understand QFT, but you really haven't seen all the beauty and nuance unless you've read this review or similar things. So this is really a great, fantastic book that I couldn't recommend more. Every student who comes to me, I tell them to read this because I think it's great. So that's I should get some royalties hopefully for that. So this is my little comment on references. Now let me kind of jump right into where we left off before. So just to recap, recall that we wanted to derive as much as we could about theories without assuming anything about a Lagrangian. And there were only three principles we wanted to use. Okay, the first principle was dimensional analysis, very simple. We all know that. The second was Lorentz invariance, and its kind of cousin, the little group covariance of amplitudes. And the third was analyticity, which was something relating to the properties of amplitudes from factorization and unitarity, which I'll talk about mostly today. Now, if you kind of look through your notes from the first lecture, you'll realize we only use the first two conditions, that is to say, dimensional analysis and Lorentz invariance, to fix entirely the three-point amplitudes to all orders in perturbation theory. We just have the expressions. So those are very powerful statements you can make just with Lorentz invariance, or in other words, just with kinematics. Okay. Now, in this lecture, we're going to use the additional ingredient, which was the third ingredient. And it takes the guise, at least at tree level, of the statement of factorization. So we've kind of gone through this in some incarnations, but let me kind of review it. So what does factorization say? Factorization says take some amplitude. We have a bunch of external particles. And take the external momenta and just tune them to a very particular kinematic regime. In particular, a kinematic regime where some intermediate momentum for, say, a massless exchange particle goes on shell. So p squared goes to 0. Now, this may seem like kind of a, well, you could do this procedure. And the statement of factorization is that had you started with some amplitude and you went to this factorization channel, then the object you'd get would have a singularity multiplied by 2 lower point amplitudes. It has very good physical sense. The physical interpretation is that for this particular set of kinematics, you're producing a state. It's traveling for a great distance through space-time, and then decaying into some other set of particles. Okay, so it's a really physical intuition for why this happens. We're just going to take that as an input here. Okay, so that's the first level of what factorization tells us, which is that there's a relation between higher point amplitudes and lower point amplitudes at special kinematics. Now, there's another thing it tells us, which I think is probably obvious, but let me just state it, which is that in terms of the singularities of the amplitude, it's not that anything goes. Some things are allowed and some things aren't. Okay, so for instance, one thing that's obviously allowed is if I just had a 1 over s, where this is a Mandelstam invariant, this is great, consistent, perfectly great type of singularity you can have lying around in your amplitude. But objects like 1 over s squared, okay, are inconsistent. Okay? And that's just because this restriction, at least at tree level, tells us that the poles should be coming from 1 over p squared types of singularities. Okay, so this is another input I'm going to use. That is something which is fixed in the analytic structure of these amplitudes and secretly encodes locality, because these singularities correspond to traveling through space-time. Okay, yes? So this, I would say, is related to the fact that when you can imagine a theory where you have propagators like this that go as 1 over s squared. So for instance, if you had box phi, more derivatives than you're usually used to. And those theories famously have issues with ghost degrees of freedom. So it's all kind of in the same wheelhouse of being something inconsistent, and I want to not include those. So indeed, there's the relationship, of course, between locality and these kind of these sick ghost modes. But if you like, for our purposes, just imagine we're imagining nice kinetic terms, d phi, and so forth. Okay, any other questions? Okay, good. So what do we want to use this for? So we constructed all the 3-point amplitudes before. We derived every possible 3-particle amplitude between massless states interacting in 4 dimensions. Our plan now is to construct every 4-point amplitude. And thus, once we do that, we'll know the entire array of possibilities for consistent 4-dimensional interacting massless particles. Okay? So this is not something that would be easy to do with the Lagrangian. If I told you enumerate every massless theory that is consistent with the principles of quantum field theory, you'd have to do a lot of work to do it. But we're going to derive all of them within the hour I have left. Okay. So what's the constraint we want to use? So we're starting at 4-point now. Okay, so we'll have all that stuff we did last time, but there's an extra ingredient, which is the statement of factorization, which I'm just going to rewrite slightly. It's a statement that in the limit where s goes to 0, s times a4, so in other words, pulling off that little singularity, should give me a product of 2 3-point amplitudes. Okay. And in everything I'm going to assume here, I'm going to assume that these are the same interactions inside these 3-point amplitudes. That's an assumption. You could, of course, imagine very complicated theories where there's much different stuff going on in either side. But I want to consider kind of a simple spectrum where there's maybe one or some multiplicity of particles that interact the same way in both of these amplitudes. Now, that's something that we'll use as an input. A corollary to this is a very obvious fact, which is the dimensional analysis of this equation. And that just tells us that we take the mass dimension of A4, then it's equal to 2 times the mass dimension of A3 minus 2. Okay. And here I want to really emphasize that when I'm counting mass dimensions, I'm only counting the mass dimension coming from momenta. Okay. So of course there is coupling constants in different dimensions. They have different dimensions. I'm factoring all that out. Whenever I talk about A's, A4, A3, I'm only talking about the kinematic pieces. Okay. Yeah, so the analogous statement is true in all the channels. Yeah, so this is just the example of the S channel. But in general, you could expect different channels that you could study. And we'll use all the channels, in fact. OK, good. So this is the only thing we'll use. And now let's derive all 4D massless field theories. And we'll start with the case of scalars. Okay, just mirroring what we did before. Now, for scalars, it's actually it's almost trivial, because as we saw for the 3-point, the 3-point interactions are already very simple. They're 1 or vanishing. But we don't even have to really assume anything about the 3-point amplitude other than that its mass dimension is not negative. Okay, so we assume that last lecture, I motivated that by saying it wouldn't make any sense for a 3-point amplitude to go as 1 over momentum. That would be highly non-local. So I'm just going to assume this. Now we can take this and just plug this into that equation for the mass dimension. And we learn that A4, the mass dimension with respect to kinematic variables, is greater than or equal to minus 2. Okay? And we'll just use this fact to derive all possible 4-point amplitudes of a scalar. And it's really just an exercise in enumeration. Okay? So what can we write down? Well, we want something which is mass. Let's start with the lowest mass dimension you can have, -2. Okay. Well, the only object you'll be able to write down, which is permutation invariant, because I have identical scalars. That's what I'm assuming. And the correct mass dimension is 1 over s plus 1 over t plus 1 over u. Okay. And likewise, you can go order by order higher. So it could be -2. It could be you could keep ratcheting up each order, and the options are pretty limited. So okay. So I'm really just writing down symmetric polynomials in S, T, and U. Now I'll leave as an exercise to you some polynomials which apparently seem to be missing, like STU, which I'm not including. But I'll leave you as an exercise to you to find out why I didn't include them. So other things like ST, STU, plus US. Okay. I'm not going to include these things. I'll leave that to you to see why. But we can now just interpret what all these things are. Okay. So this first thing is pretty obvious. Okay, 1 over s plus 1 over t plus 1 over u. On the factorization channel, we just multiply by s, take the limit, we get 1 times 1, which is precisely what we had for the 3-point. Nothing surprising. This is just phi cube theory. Okay. Now, crucially, well, not crucially, but you can just see manifestly, this is the only theory that has singularities. Right? So all these other things, when you take s goes to 0, t goes to 0, u goes to 0, they're regular. Okay? What that means is that their factorization channels give vanishing 3-point functions, which is exactly the case that we studied in last lecture, where A3 could be 0 or 1. Okay. So these all have other names. This is just phi 4 theory. This we saw before. This is actually 0 because of st plus t plus u equals 0. But if you wanted to write it as a Lagrangian, you could, of course, write d phi squared times phi squared. And likewise, it's easy to see that this guy is just 4 phis and 4 derivatives. And this last guy is 4 phis with 6 derivatives total, just from dimensional analysis. Okay? So you might ask, though, how do I know how to contract these various Lorentz indices? Right? If I gave you 4 phis and 6 partial derivatives here, you'd have many ways of contracting them. And you'd say, well, how do I know what objects I'll get out? Well, it turns out you don't have to compute it. You don't have to do any hard work. There's simply no invariants you can write other than this. Okay? So you can write all the different structures you want, and they're all in the Untitled amplitude, end up giving you these, this structure for A4. Okay, and we can keep going. I'll mention a little bit later why it's actually, this is the full body of things that will be interesting. But as you can see, we've kind of restricted things a bit, but not enough to kind of give these any kind of meaningful names, right? To us, this is a Goldstone boson Lagrangian. This is kind of a Goldstone boson Lagrangian on crack. But it's all just a bunch of derivatives on phis. Okay, so we don't actually learn that much about scalars, and that's OK. That's just a fact, given the input we've inserted so far. Okay, but this is the story for scalars. This is every possible 4-point amplitude you can have for scalars. Questions? OK, so that's the very simple dimensional analysis story for scalars. For vectors, it's actually much more interesting. And we'll learn something actually deep. OK, and I'm crucially here saying just massless vectors interacting rather than assuming that it's Yang-Mills or anything. Let's just see what we get at 4-point. Okay. Now, from last time, you'll recall that A3 for the Yang-Mills vertex, which we identified, was mass dimension 1. Okay? It kind of eats up all that covariance. So what we're going to want to do is write down some object which has all the little group covariance just stripped off. Okay? And it's not too hard to see what that has to be. After all, for this amplitude, when A4 transforms under the little group, then we know that this transforms as T1 squared, T2 squared, T3 to the -2, T4 to the -2. Right? Just the power of the helicity, and the helicities are minus, minus, plus, plus. So you just want to write down some object which manifests this covariance. And it's not hard to see that the only thing you can write down has 2 angle brackets for 1 to accommodate this guy, two angle brackets for 2 to accommodate this guy, 2 square for this, and 2 square for 4. Okay. Now, of course, this can't be the whole answer because I can now multiply this by an arbitrary function of a little group invariant. Okay? And I want to be totally general, so let me just write down that little group invariant function and call it a function of ST and U. Okay. So there's stuff in the denominator, numerator, any kinds of things, okay, in principle. Okay, and this is our general ansatz. Well, it's the only ansatz we can write down which can manifest these little group properties. But it's got a big function here that we want to understand and fix. Questions? OK. Now, what do we know about FSTU? Well, okay, so keep in mind, we know that the amplitude, A4, is dimensionless. But we've added this little prefactor to absorb the covariance. What's the dimension of that prefactor? Well, each angle bracket in square bracket is like the square root of momentum. So this goes as something like p squared times p squared. Right? So this whole thing has mass dimension plus 4. Okay, just from this first term, which means that FSTU has to have mass dimension minus 4. Okay, so we want to write down an object which has mass dimension minus 4. Let me write down the ansatz and then justify it. Or I should really say the general solution. OK, so where did I get this? Well, permutation invariance that we had in the case of one single scalar is no longer afforded to us because we have another label, A1, A2, A3, A4. So I'm not going to assume anything necessarily relating these different coefficients. The reason why I put 2 factors of Mandelstams is I want to construct some object which has mass dimension minus 4. And crucially, the types of terms that I have missing, you could ask, are things that look like 1 over s squared. Okay? Double poles, which we've thrown out. Okay, so I have specifically chosen only objects which have a single pole at most in any given Mandelstam invariant. Okay. Now, for dimensional analysis, here, of course, I'm assuming that the dimensionality of CST and CTU and CUS is vanishing. So these are just numbers. CUS, CTU, CST, these are just numbers, constant numbers. Okay, this is our general, the general solution to what F, the form that F can take. OK, any questions? OK, so what do we do now? Well, let's fix these coefficients. With what? With the one extra bit of information we have, which is the factorization channel statement. Okay, so let's look at the case of factorization in the S channel. Okay, put 1 and 2 here, and then 3 plus and 4 plus. And I imagine that these guys are tuned such that this intermediate leg is on shell, which is just another way of saying that S is going to 0. Okay. And now we can solve for the coefficients. So we want to take the limit as S goes to 0 of S times A4. What is that? Okay, so, well, we have F as a function of ST and U. We can just ask. So we have this function, multiply it by S, and then take the S goes to 0 limit. You'll see that there's only 2 terms here that are singular. So recall, so as I send S goes to 0, then T actually approaches minus U. Okay. So this middle term is just a regular term. It's not singular. And these 2 terms end up becoming singular. And they get picked out by this limit. So multiplying by S and then taking the limit, we get 1 over T times CST minus CUS. In those 2 terms. And we want to compare this now to the correct answer. Okay. By the correct answer, I mean actually taking the 2 3-particle amplitudes that we derived last lecture and just inserting them into this expression. Okay, so what should we do? Well, first we should recall that in a factorization channel, you should be summing over all the possible states that can be exchanged, plus or minus. Okay, but in our case, it's just naively plus minus or minus plus. We actually studied both these cases in last lecture, and we realized that the minus minus plus corresponded to the Yang-Mills vertex, which is what I'll keep. The other case was minus minus minus, which is a higher dimension operator that you could choose to keep, but I want to restrict it so that's not included among the 3-point amplitudes. I don't want to include that higher dimension operator. So I'm only going to keep one of the factorization channels, where that's a plus and a minus here. So I'm going to keep this combination. And the other one, in fact, you could have, we could add it. I welcome you to add it if you are interested. But we won't do that in this case because we care about constructing Yang-Mills. Or I shouldn't say Yang-Mills, constructing the vector corresponding to that 3-particle amplitude we started with. OK, so what do we get? Well, we have an A3. We have 2 factors of A3. And there's a 1 minus, 2 minus, 3 plus, 4 plus. But now I have a new leg, which I have to add, which is the intermediate leg, which I'll call P. Okay, so this is the momentum here flowing, which I call P. And again, I have to recall that there is actually subscripts here, A1, A2, A3, A4. And now, of course, P has its own index, which I'll call B. Okay. Now, from last lecture, we saw that we had to add coupling constants, which went as FA1, FA2B, FA3, FA4B, corresponding to each 3-point function. So these are just parts of those 3-point functions. And I need to sum over all B. OK? Any questions about that? OK. So what do we get? Well, the structure constant piece is simple. A1, A2B, F, A3, A4B. And then a bunch of, well, let me just plug in the explicit expressions for these amplitudes. OK, so recall this is, oh, I should have put a plus here, a minus. So this first guy was the MHV 3-point amplitude, which is all angle brackets. The second guy was the MHV bar amplitude, which was all square brackets. So I just plugged in the expressions we had from last time. Okay. Now it's just a bit of algebra to simplify this. Let me just quote the answer, but then I'll leave it to you as an exercise to show. This whole object can be simplified into 1, 2, 3, 4 squared times 1 over t. Okay, and here's the trick I use. Okay, so this p here, the only kind of foreign object in this expression is p, right? Because if I give you angle brackets and square brackets of 1, 2, 3, 4, you know how to construct st and ut from it. Okay, that's not the hard part. The thing that may puzzle you is this p. But what you want to do is take p and just replace p with 1 and 2 because we're on a factorization channel. So in particular, we know that p is equal to, or minus p is equal to p1 plus p2. So, well, just as an example, you can take a term that looks like 1p, like this, 1p, p4. Okay, this is an example. Take 1p and p4. Let's forget this. You can rewrite this as, let me write it in full gory detail, as 1 alpha, p alpha alpha dot, lambda tilde 4 alpha dot. Okay. And then you can just take p and replace it with minus p1 minus p2. Okay? Once you have everything in terms of p1 and p2, then you can write everything back in terms of their angle and square brackets, and then you can simplify. Okay? So that's the workflow for actually doing calculation in this case. Take the p, which is intermediate, and rewrite it as external momentum. Okay? You can always do that. OK, good. Any questions about this? Sorry? Oh, can I? Oh, you can't see. OK, good. So, well, actually, I need to point out something. Let me say this before I move on to the next board. Well, we have 2 expressions that are the same, and they look almost identical, right? 1, 2, 3, 4 over t. And then this this last piece, CST minus CUS. Okay. So what does this mean? This means we can, of course, just solve for these C's. Okay. What do the C's equal? Well, they equal this prefactor of the product of F's. Okay. We can just identify the terms. So let's do that, and we'll find something kind of remarkable. Okay, so we can do that in the S channel, and we get a simple formula, which just tells us that CST minus CUS equals sum on B of F A1, A2, B, F, A3, A4B. Okay. Do the same thing for the other channels. I won't do it, but I'll leave that as an exercise for you. You'll get similar looking objects, right? And you'll just kind of keep comparing term by term. And you'll find CTU minus CST equals sum on B of F A2, A3, B, FA1, A4, B. And the last equation, CUS minus CTU equals sum of B, F3A1, B, FA2, A4, B. Okay, so it's a bunch of kind of complicated objects, but the origin of the structures is simple. The FABCs are encoding which factorization channel you were looking at. So here we were looking at the 1-2 factorization channel, here 2-3, and here 1-3. Okay, so that's all that is. And we have a set of equations that we want to solve now. Okay. Is it clear, at least conceptually, how I can get here? Now you'll notice something that is not an accident, which is, let's say, just sum all three of these equations. Okay, just add them up. These three terms cancel amongst each other, giving me 0. And we get, let me write this in shorthand, we get the statement that F, A1, A2, B, well, let's write it out, A3, A4, B, plus the permutations 2, 3, 1 plus 3, 1, 2 equals 0, which is the Jacobi identity. Okay. Now notice, well, this obviously wasn't an accident. You've seen this before. Where have you seen it? You've seen it because normally when we compute this object, we would have said, take a Lie algebra, compute the trace, let's see, TA1, TA2 times TA3, TA4. Okay? And you say lots of words that are great, true about Lie algebras, SUN, what have you, all these statements. They're all great and true. But you may have maybe misinterpreted that beauty as meaning that it could have been any other way. Like there was a second option other than the Lie algebra structure of antisymmetric structure constants that satisfy a Jacobi identity. There's no other way consistent with factorization, Lorentz invariance, and dimensional analysis. Okay? So that's actually, at least to me, I find this to be amazing. Okay, I skipped all the middle chapters of the main QFT textbooks and just derived what was supposed to be a math statement, but it's really coming from a physical principle, which is factorization. Okay, so I think there were a lot of excellent questions, maybe from last lecture, where people were saying, well, how do you know which gauge group it is? You know, is it SU3, SU3 cross SU2 cross U1? Well, all that matters is that the constraints I impose are the set of constraints that Lie algebras have to satisfy, and Jacobi is of course the primary one. Okay, any questions about that? Okay, let me mention a very cool miracle also about this, which will foreshadow what we'll see in the next lecture. Yeah. We didn't have this. Yeah, so we didn't have this because, for 3-point, because the Jacobi identity intrinsically involves four things. A1, A2, A3, A4. So what we had from last time was just that we had an F that was an antisymmetric. So this is an extra ingredient that we need.
Whenever you say factorization, you say full point, you make full point and 3-point.
That's it. That's all I mean, yeah. In S channel, T channel, and U channel. Exactly. Okay, good. Very good. So let me note one more thing, which will look like a complete miracle, but is true and will foreshadow some of the sorcery that I alluded to in the first lecture and we'll discuss in depth in the last lecture, which is the following fact. Okay, so I've told you that these conditions fix the structure constants to have Jacobi relation identity. But let's solve for the amplitude. Okay, let's just solve for C's in terms of the F's, plug in and get the amplitude. You can do that. Okay? But you'll already notice something interesting. Okay? Let's say you just took these equations and tried to solve for the C's. Okay? You'll realize there's a flat direction. There's something which isn't fixed, and it's pretty obvious what it is. Take a C and just shift it by constant. Okay? Take this C, shift it by some number, and take this guy and shift them by the same number. So take all the C's and just shift them by one fixed number. Okay? So very explicitly take CST. Okay, so this isn't an operation in any field theory sense, but just in the equation, just imagine doing this. Then you'll find that this is obviously an isometry of this construction of this equation that I just solved for, where Z is arbitrary. Okay, so Z could be a number, but who knows? Maybe Z depends on momenta. Z could be anything you want. It doesn't matter. These equations don't even see it. Now that seems very confusing. Okay, how could that be possible? You shift it. I now have Z dependence. I plug back into my amplitude, and now my amplitude Z dependent. Right? That's nuts. But you have to keep in mind that under this transformation, A4 will shift because, well, you can just plug in the transformation up there. And you'll find that the Z dependence is proportional to S plus T plus U over STU. Okay, just each of those terms, if I just rationalize them together, gives me something which is 0. Okay, so it's a statement about just taking the numerators and shifting them. I'm not telling you how I was able to do that, why I did that. But if you chose to do that, the amplitude would be invariant under that transformation. Okay. Now, the reason why that is a little bit miraculous is that this Z could be any function you like. So in particular, it has a physical meaning, well, a physical correspondence given what I said last lecture. Okay, so here's what it means. Imagine you took Yang-Mills and you chose to compute the amplitude in a given gauge with a given Lagrangian. Okay. Now you take Yang-Mills and you change gauges and you do a field redefinition and it's all scrambled. You should get the same final answer. The answer should be the same. The different Feynman diagrams will be different. Okay, like the separate Feynman diagrams will all change, but the sum answer is the same because it doesn't affect the physics. This Z contains all that gauge covariance. Okay, this is the statement that each numerator is not gauge invariant. When you change gauges, they all change, but exactly in a way that conspires to give the right answer in the end, because it doesn't matter. Okay? In particular, you could imagine that Z involves hundreds of derivatives. Do a field redefinition. A mu goes to A mu plus some insane function with 100 derivatives. You would just dump new derivatives here, and it wouldn't affect the answer. You can just see it. Okay. Now, this relates to a, well, we'll get ahead of myself, but we'll use this fact a little bit later. Okay, any questions? Okay, good. So that's it for Yang-Mills. We now know that the only theory of interacting vectors, massless vectors in 4D is Yang-Mills. There's nothing else. Let's move on to tensors. So naively, this should be the hardest case, right? Gravity's hard. Who knows what's going on with gravity? It's, you have to think really hard, write Lagrangians down, think about geometry. Well, that's actually not the case either. As you can see, we can just repeat our workflow. Questions? Okay. So what do we do for gravity? Yeah. Oh, yes. You're good? Okay. Cool. Sounds good. So let's go to tensors. Okay. Let's do exactly the same thing we just did. So we take A4. This time I have minus 2 helicity or plus 2 helicity, which I'll write as double minus and double plus. Exact same prescription. Almost nothing has changed, except the little group weight is doubled. Okay? You double the little group weight, just double the ansatz. So we have here 1, 2 to the 4th, 3, 4 to the 4th. Okay, just carrying all the little group weight times a function fstu, which I want to solve for. Now recall, I should have written this down before, that, well, the 3-point amplitude, just from dimensional analysis, is two-dimensional. Right? There's two derivatives in the graviton, 3-point function, but we also just derived that, so we didn't need to know that. But this implies that A4 is 2A3 minus 2, which is 2. Okay. So the total mass dimension of the graviton scattering amplitude in 4 dimensions should be mass dimension 2. Again, we can just count. So recall, each of these angle brackets is like a momentum in terms of its mass dimension. So this is p to the 4th, p to the 4th. And I want p squared at the end. So I need p to the 6th in the downstairs. So I have to write down a function fstu, which just has the right mass dimension, dimension minus 6. And there's only one, stu. So we saw this, I think, in one of the earlier lectures. You might ask, why don't I write down other things? 1 over s cubed, 1 over t cubed, 1 over u cubed. Well, those things are forbidden by locality. Okay, the prescribed analytic structure forbids those. So we're left with what is indeed the 4-point graviton scattering amplitude in 4 dimensions. This is the fastest derivation you'll ever see. If you try actually deriving this from Feynman diagrams, it'll probably take you, probably at least a week, I would say. So recall, this is the theory where each 3-point vertex is 120 terms. You multiply them together, massive redundancy. It's just a single term, and this is indeed the answer. Okay, and of course this probably should look familiar from Nima's earlier lecture discussing ultraviolet completions from gravity. Okay. Good. So to be honest, that's the coupling constant. So how do you fix it for Yang-Mills? How do you fix it for gravity? It's G Newton in this case. Right. But I will say that, like, for the most part, in everything I'll do, we're going to be dropping, so what I'm saying is, what do I mean? A3 has an unfixed normalization, right? We just threw out the coupling constant. If you put that back in, that will enter into the factorization relation, which will tell you what the coupling constant is at 4-point. Okay, so that's why, if you may have wondered in Yang-Mills, there's a g squared a to the 4th piece. How does he know about g a cubed term? It's because they're related by gauge invariance, of course. So it's exactly connected to this statement. Was there another question? Yeah. Yeah. Right, so this is actually, gravity just turns out to be nicer than the case of gauge. So indeed, this has no diffeomorphism redundancy in it at all. There's no redundancy, right? There's nothing you can change and twiddle. And in that sense, this is truly the first time, I think, for most of you, that you've seen a graviton amplitude without any of the redundancy. For the case of the gauge theory, just in the way I parameterized the fstu, there was still a little bit of a remnant. But I assure you, there's a way of writing down the Yang-Mills amplitude where even this redundancy is gone, and it actually will connect to what I'll discuss in a little bit. Yeah. Any other questions? OK, good. So let me mention one last thing, which is really just an exercise for you to prove something that was very hard and took a lot of thinking from great field theorists, but for us will be absolutely trivial, which is, or for you, it will be absolutely trivial, which is, what about spin 3 massless? Okay, not helicity plus minus 2, but helicity plus or minus 3. Okay. So this is a little exercise, if you like. Prove that this theory cannot exist consistent with all the things we just discussed. Okay? It's almost a one-liner. I won't bother going through it, but it's instructive. You can see by the same mechanics, you can show what takes a huge amount of work if you were done a Lagrangian. Right? If you were done a Lagrangian, you'd say, massless spin 3, let me gauge fix, do this, do that, symmetrize my indices. It's hell on earth. So instead, you can just compute this on your own, and I assure you that you will find something interesting. OK, any other questions? Yeah. Let me not say what the idea is, but that's certainly the right track. Yeah, that's right. I don't want to tell everyone what the answer is yet, but you're definitely on the right track. Yes. Oh, good. So I could really choose to pick any. I wanted to construct the leading 4-point amplitude that would really the most transparently translate into the 3-point amplitudes. But you could take other combinations, and you'll find actually some interesting things. So if you fixed all minus and tried matching it to factorization, you'll find some disagreement that would imply that certain things are 0. In fact. So I'll leave that to you as another exercise. So consider, all minus. Okay, all minus. Okay, and just ask whether it can be consistent with factorization into the 3-particle amplitudes that we built for Yang mills. Okay? It's another simple exercise to see why some helicity combinations vanish and some don't vanish. Just to cut to the chase. Okay, let me try to accelerate because I think I'm super behind. Which is I'm now going to talk about generalizing this whole setup. Okay, so I think now I've convinced you, at least, well, I think this is just the argument that we have enumerated every possible massless, a theory of massless particles that interact in 4 dimensions. But you could still ask, well, that's great, but what about 5-point, 6-point, 7-point, etc., right? Who knows? Maybe I keep working at this, and at 77-point, it fails. And then it stops working, and I have to pull out my Lagrangian and cheat, okay? We don't have to, fortunately, because there is a kind of less case-by-case, less artisanal way of constructing the S matrix, which is to automate this entire procedure. That procedure is known as recursion, okay? And I'll now discuss that. So which thing were you asking about? So the what? It won't. So if you did this, it wouldn't fail. But to the devil's advocates in the audience, maybe you'd say, well, this is 4-point. Things are easier there. Maybe when you have many factorization channels, it fails. You could wonder. But I'm going to give you a proof for why you don't have to worry about that. Okay. I mean, I can't just assert that. I'd have to show you. So let me show you. By proving that with this low-point data, we can construct everything in the case of these gauge and gravity theories. What is the essence of recursion? So recursion is based on a very simple principle, which is essentially to automate this factorization statement. Okay. So they're just saying I'm not going to be able to count properly, but you have some amplitude. We know that it's related to some lower point amplitude on factorization channels. But of course, the external kinematics for a given amplitude you're handed isn't at special kinematics, right? If I just give you some LHC amplitude, it's at some generic configuration, okay? So we don't get to send any p squared goes to 0. They're just fixed, okay? So let's say I really want to ask you about a general kinematic, an amplitude of general kinematics. How do I probe those factorization channels? The external momenta are fixed, okay? The essence of recursion is actually quite simple at its heart. The idea is to take an amplitude which starts out with some fixed momenta that you're given, initial momenta, and deform them in a certain way. Okay? So you see this all the time in the old analytic S matrix program where they would take S and complexify it and imagine studying the function in terms of S. And that's great, that's fine. But much of the progress in recent memory in the modern amplitudes program has been to realize there's actually a lot of interesting ways to actually probe these kinematics. And that has to do with something called momentum shifts. Okay. So for momentum shifts, what do I mean precisely? Well, you could always, to probe the amplitude, just take literally all the external p's, p0, p1, p2, p3, and just like move them around. That's a rather, kind of a too blunt of an instrument. There's a nicer way to construct these shifts, which is to take each pi and shift it by some parameter, some four momentum kick multiplied by a parameter z. Okay, so it's like these are the initial momenta, and now let me just kick it in some direction qi, but proportional to some z parameter. Okay, so z moves you in the kinematic space. It lets you kind of twiddle around these external legs as a function of z. Okay. Now, of course, as a result, A will become a function of z. So now the amplitude is a new one-parameter function of this deformation parameter z. And qi are a set of 4 vectors. Okay. Now, the first thing you should ask is, well, how can you just kick things around? You can't. There's constraints on the qi because we want to maintain on shell the entire way. What do I mean by that? Well, it's not going to help us very much if this thing kicks us in a way that doesn't conserve momentum or doesn't conserve the on-shell properties of the amplitude. After all, the entire purpose of the recursion is to write everything in terms of on-shell quantities. Let me add the Lorentz subscript too. So, yeah. Thank you. So I here is a label for each leg, and mu is the Lorentz subscript. Thank you. Yeah. That's right. That's right. Thank you. OK, good. So, but there's a constraint on these. Right? Why is there a constraint? Well, we want to make sure that after you shift by z, for any z, you still conserve momentum and are still on shell. So that places an obvious set of constraints. Well, the sum of qi over all the guys you've shifted better be 0. That's just momentum conservation. So by momentum conservation, I mean that for all z, for any z you choose, momentum is still conserved as long as these guys sum to 0. And then there's a second constraint, which comes from the fact that if you look at the on-shell condition for the shifted momenta, you want to make sure that those are still on shell. So for instance, if I just take the shifted momentum and square it, you get pi squared plus 2z qpi plus z squared qi squared, okay, being as general as I possibly can. And this thing has to still be true for any z. Okay, and this just places a constraint on the qi's and the pi's, which are that qi squared equals qi pi equals 0. Okay, so there's this condition, momentum conservation, and a second condition, which is on shell. Okay. But qi has lots of degrees of freedom in it, so we can solve these. Okay. You can imagine just taking a set of momenta p and then solving for these qi's, and you can construct them. Okay? But the point here is now we have a z parameter that floats around in space. We can move it to any value of z we want, and we maintain on-shellness, momentum conservation, but we can still probe the kinematics of the amplitude. Okay? Now, what's the point of this? Well, the point of this is by introducing z, we can now probe factorization channels without changing the original external kinematic data. Oh, why are these two things 0? So you can think of this as an equation that has to hold for any z. So this guy is automatically 0. So this term has to be 0, and this term has to be 0. Yeah. Sorry. OK. Very good. Now, what is this bias? Well, imagine you were studying some subset of momenta, which I'll say are contained in a set I'll call I. Okay, so I is a set of the external legs, and I'm imagining, I want to study some factorization channel involving the pi, which corresponds to the sum of all momenta with I in I. Okay, so this is just the sum of all the momenta flowing through this line. Okay, so I'm just taking the particles and splitting them into two groups. One I call I, the other is the complement of I. And let's say I want to probe this factorization channel, but I can't actually change these momenta. I have to use my function of z here. Well, the point here is that when you deform the momenta, pi becomes a function of z, which is now just the sum of I and capital I of pi of z. Okay, a sum of deformed momenta. And while in general it's true that p squared is not in general equal to 0, right? As we were saying, we're in general kinematics. We're not assuming we're on a factorization channel in the initial kinematic data. But despite this fact, we can ask, when is it that p squared of z equals 0? Okay? We can study for what values of z we can hit the singularity by scanning z to the appropriate place. Okay? In fact, we can define that z as a point in the complex plane for z, which when you hit it, this pi squared vanishes. Okay? So in other words, we took a given factorization channel, momentum deformed it, and now we're going to twiddle z around until we can actually hit the singularity. And we can do that because z is just a free parameter. Okay? Now, what does this mean? Well, the statement of factorization is a statement that the limit of pi squared of z as z goes to zi of a of z, right? I'm just rewriting the factorization statement. This thing should equal a product of two amplitudes, which is the left amplitude and the right amplitude, but evaluated at zi. Okay, so this is just a restatement of the factorization we used before, but the only thing that's tuning me to that factorization channel is this z. Okay. Now, why is this useful? Well, it's useful because when I say that there's a singularity, in complex analysis, as you know, that actually can be very useful. Singularities are poles. And with poles, you can, well, of course, do a lot with the immense machinery of complex analysis, in particular Koshi's theorem. Okay, and the kind of key thing that we'll use is the fact that if you look at the residue, right, so the kind of complex analysis way of saying this statement of the limit, is that if you take the residue as z goes to zi of a of z, then this is proportional up to some various Jacobian factors, which we'll be careful with a little bit later, to just the product of ar zi. Okay, so this has just been a kind of a formal way to say something really stupid, which is that if you take the momenta, parameterize some space where they move around by z, then when z hits certain points, the residue of the amplitude decomposes into subamplitudes, lower point amplitudes, and that's the requirement of factorization. I haven't gotten there yet, but don't worry, I will get there in the next 5 minutes. Jeez. Wait, how much time do I have? No, I have more than that. I have more than good. 20 minutes. So just much less time than I need. OK, so let's use this, and let's consider the most famous incarnation where this is true, which is the case of gauge and gravity theory. So everything I've said is very agnostic about the theory, but let me just quote, say that I'm going to study gauge and gravity theories, which were studied with this set of recursion relations under the name of Bcfw, Brito-Kachazov, and Witten. And it's really like the most minimal thing you could do given this picture. Okay? So imagine you want to deform some momenta. Well, what's the simplest thing you can do? Well, deform one momentum. Well, that doesn't work. If you deform one momentum, you can never satisfy this conservation law because you can't counterbalance with another momentum. So the minimal thing you can do is shift two legs. Nothing less exists. And the momentum shift that Bcfw is based on is just the following. Okay, so there's just one q. I add it, I subtract it. Momentum's conserved manifestly. And at the same time, I have to constrain q such that qp1, qp2 is equal to 0. That's just the on-shell condition. Okay. Now let me mention one thing, which is that in terms of, so this, as you can see, is actually just a general any-dimensional statement, right? I didn't say anything even about 4D, which is why Bcfw recursion exists in any dimension. Okay, so I'm not bound by any statements about spinor helicity, etc. Okay, those are irrelevant. But let me just comment that in spinor helicity form, this shift has a very kind of nice form, which is that you want to take lambda 1 tilde, which is just p1, and shift it in the following way, where lambda 1 tilde gets shifted by z times lambda 2 tilde, and lambda 2 tilde gets shifted by lambda 2 minus z lambda 1 Okay, and this may look kind of arbitrary, but all you have to do to derive this, this constraint is set q equal to lambda 1, lambda 2 tilde. Okay, so if you just write these in spinor helicity variables, plug that in, you'll find that that's equivalent to this statement. So it's just a particular choice of q. Okay. I actually won't use that at all, and it won't be important for what I have to say for the most part, but I just thought I'd show it to you. Okay. Now what do we do? So here's where I can now tell you the real meat of Bcfw and recursion relations in general. It's actually extremely simple, beautiful principle, which is let's construct the amplitude from its factorization channels. Okay, so what's the amplitude? Well, of course, by definition, the amplitude is a of z when z equals 0. Okay. What is a at z equals 0? Well, of course, I can just write this as the integral dz of a of z over z 1 over 2 pi I over a very specific contour, which is encircling z equals 0. Okay, this is like a massively trivial statement. I'm just saying wrap, do this contour around 0. It just picks up this pole, which sets a z to a z at 0. Okay, total triviality. Okay. Now, where is the non-trivial aspect? The non-trivial aspect is, of course, the fact that we can apply Koshi's theorem. And crucially, I'm going to assume tree, like I've been doing for this whole lecture, which is that there's a fixed singularity structure such that they factorize according to this type of residue theorem. Okay? So all the residues of A, its poles in the z-plane, are actually related to lower point amplitudes. So we can just blow up the contour and extract all the other terms. Okay? So let's say you do that. Well, just formally, you can write this as the sum of residues. So here I is going to sum over all the different residues that exist. A of z over z plus, and this will be actually important, of course, a boundary term at infinity. Okay, if I take this contour at 0 and I blow it up, I'll pick up all the poles in the bulk z-plane, and then, of course, there's some giant arc at infinity that, in principle, we have to worry about. Okay. Now, let me postpone this actually crucial, but for the moment, an element that will only confuse us. Let me ignore this for the moment. Okay? I'll justify that later. Okay? Let's just consider what this expression gives. Okay, and you can even see what's going to happen. Okay, this is going to pick out the residues everywhere except z equals 0, because I blew it up over z equals 0. So it's just going to pick up the residues of a of z. You pick up the residues of a and z, you're just going to get products of these objects. Okay, so let me accelerate slightly and just write down the answer, because you can just see what's going to happen. Essentially, well, each of these residues, let me write down one equation. Z equals zi on the factorization channel. There's a 1 over z, and then there's going to be some a left of z, some a right of z, divided by pi squared plus 2zq dot pi. And this bottom thing is nothing other than pi squared of z, where the q squared piece is vanishing because of this condition, the on-shell condition. Okay. So using this, you can realize that on each residue, you can replace this with this object and then just compute what the formula is. And it gives us our final expression in the limit that we can ignore that pesky boundary term. And this final expression is the so-called Bcfw recursion relation. Any questions? OK. Very good. What is it? So the amplitude, which is just a z equals 0, is a sum over all I of 1 over pi squared. Okay, so I want to emphasize this pi squared is not pi of z squared. It's just the original pi, okay, which is not, pi squared is not 0, because I'm not at special kinematics for the original momenta. Factor of pi squared times a left of zi times a right of zi. Okay. Now, what does I sum over? I sums over all possible poles you can get. Okay? So when can you get a pole? Well, let's just consider the different topologies you can imagine where factorization occurs. Okay? Now everything is more or less permutation invariant, except we picked two legs to be special, 1 and 2. Right? We shifted 1 and 2. No one else was shifted, so 1 and 2 are somehow preferred. So we should care where 1 and 2 are. You can see, obviously, that if I have 1 on this side and 2 on this side, then there's a flow of z-dependent momentum through this, right? Because this is shifted by zq, and the zq has to go somewhere, so it flows out this way. Okay? Thus, for these types of diagrams, there is a singularity that you can pick out. This moving z around can actually pick up this pole. Okay? Now, of course, there's other terms you might wonder about, which is, well, what about when 1 and 2 are on the same side? Okay? When 1 and 2 are on the same side, well, plus zq and minus zq cancel. So there's no z dependence through this at all. So here's what's amazing. In terms of the diagrams I, this thing is contained in I. You should sum over these factorization channels. But you should not sum over these factorization channels. So these guys are not in the summation. You do not include these factorization channels when you sum. Okay? So that's not a new rule. That's just us realizing where the singularities happen. Now, if you think about it, that's rather amazing, actually. Because when you use Feynman diagrams, every factorization channel is just there. You can see it. It's in the diagram. You write this down. When you tune the momenta, the 1 over p squared in the Feynman diagram would diverge. Right? The one thing that's great about Feynman diagrams is that every factorization channel just manifestly blows up where you want it to. In the case of Bcfw, it's much more hidden where the factorization channel is. Why do I say that? Well, some factorization channels are obvious. Pi squared here is obvious. It's just right there. It's like a Feynman propagator. But other channels, which are there, other factorization channels, like when 1 or 2 are on the same side, are not manifestly in the expression. Okay? They're not there, but manifestly, but of course in the whole sum they exist. They're present. So if you take 1 and 2, you look at this factorization channel on this expression, you'll still find a singularity. It's just that the singularity won't be as dumb as just a 1 over p squared. It'll be a whole sum of terms which conspire to give you a 1 over p squared that blows up. So oftentimes people say that Bcfw actually obscures locality, and it's exactly for this reason. Right? It may seem confusing because I use locality and factorization as the input, but you have to keep in mind I only inputted factorization in some channels, not all of them. Okay? There are channels where it's much less obvious, and that's a real miracle, at least from the point of view of this formula, why it gives the right answer. But of course it does, because we just use complex analysis. Okay, any questions?
So if you choose different choice of vector, you should be able to see the manifest locality.
Yes, exactly, precisely. So you could, if you wanted, do the hard work of shifting 1 and 2, and then 1 and 3, and then every combination. And there would be different forms where different factorization channels were manifest. But in any choice you make, there will be other ones that aren't manifest. Okay? So that's what's so cool about this. So when people say, people not like me, say more haughty-taughty words about dooming space-time, this is like the first sign of that, which is that the 1 over p squareds aren't there. The objects you get are much more foreign. Okay? In fact, well, let me even say, you can use this. Sorry, you can use this expression to derive the famous n-point MHV amplitude, which is a single simple formula for all gluon amplitudes of a given particular helicity configuration. I'm not going to tell you all the detail of this, but just to show you the power of this formalism, you can, by recursing inductively from 3-point and up, you can derive the fact that if you take a gluon amplitude, because I've called them A, gluon amplitude with, say, a bunch of minuses, okay, until you hit 1 plus here, and then, 1 plus, maybe it's plus. Okay, so the idea is that these are all pluses, okay, except for 2 guys who maybe even are separated by more pluses. But there's only 2 legs here that are minus. There's a beautiful, gorgeous formula, which is kind of what theorists dream about writing down but never are able to, which is this whole thing collapses into the following beautiful string. Okay, where the top is just ij to the 4th, and the bottom is just a set of cyclic products. Okay. I've stripped off the color structure for the moment. Don't worry about it. But this is just a beautiful expression you can get just by using it. Okay. Now, of course, if you derive this with Feynman diagrams, you get thousands of terms. And you would still have it in terms of polarizations. And you never see this. And there's actually a very interesting history behind this formula. But even just looking at it, you can already see it kind of smells right? You can, an exercise I give you is to study the little group properties of this. Check that this could be an amplitude. Make sure that it actually has properties that I argued should be had for an amplitude. OK, yeah. Question? Good. Yeah. That's a great question. I will cover this actually in next lecture. But the idea is that you can take Yang-Mills amplitudes and decompose them into fixed color structures, where the ordering is fixed by certain ordering of colors. If that made no sense to you, the beginning of next lecture, I'm going to go through that very, very in great detail. Color ordering of the amplitude. If that meant nothing to you, don't worry. I will go through it very, very, very carefully next time. But let me try to accelerate a bit. So notice there was an elephant in the room.
Before you accelerate?
Yeah.
Okay. So everything here is tree graphs.
Yes.
Okay. So let's back up. There is a crucial point where there is a statement that you made. Okay. And then the answer is going to be all tree graphs and not in the talk about these. What is that statement? The statement that the electricity properties of the scattering entities are only poles?
Yes, that's right. Yeah. So the question was when did I assume tree here? And it's precisely that I assumed that I could apply Koshi's theorem, where the residues only extract simple poles in each C. Now, I assure you there's any array of very interesting things you do at loop. I, of course, don't have time for that now, but I'm happy to tell you offline about them. Let me now mention this B infinity, okay, the boundary term. The B infinity is something you'd have to worry about, and in general, it's there in a given theory for a given amplitude. Here is the amazing fact about Yang-Mills and gravity. So in some sense, this is a structural statement about the theory that didn't have to be true, but is true, which is that I can choose, well, when I do this Bcfw shift, as long as particles 1 and 2 have a certain set of helicity configurations, then this B infinity actually is 0. Okay? So what do I mean by that? Let me elaborate. So what is a simple condition to make B infinity vanish? Well, obviously, if A of z, when z goes to infinity, is 0, then this is at least a sufficient condition to make B infinity equal 0. Okay? Now, in the game of amplitudes, people talk about momentum shifts, and much like people, they come in two kinds. There's the good shifts and the bad shifts. The good shifts are the good shifts where that B infinity is 0. And the bad shifts are the ones where it isn't 0. Okay? So you have to be smart. You can't just pick any willy-nilly shift. You have to be smart about it. How do you have to be smart about it? Well, it just depends, in this case of 4D, on the helicities of legs 1 and 2, if I choose to shift it this way. So okay, so for the combinations where 1 and 2 have minus, 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 plus, or plus, plus, then this shift beautifully has the large z behavior vanish. But for this bad shift, it will not vanish, and you'll be in trouble. Okay? Now, I wish I had time to justify this to you, but there's at this point like any number of ways you can understand it, both with Lagrangians and also just within amplitudes by rewriting the boundary term as other factorization channels. But there's a nice intuitive picture, which I'll just briefly mention, which is that you can determine which is a good shift and a bad shift by doing something very physical, which is to imagine that when you have a scattering amplitude with two particles, 1 and 2, that are very hard, P1 plus ZQ, P2 minus ZQ for a large Z, that it really corresponds to some particle that's super hard streaming through some soft gas of other stuff. Okay? So you can really think of it as a soft background of the rest of the amplitude with some hard particle streaming through. Okay? Now in field theory, you can just study those amplitudes in background field gauge and deduce these properties. You can do this in theories beyond gauge theories and gravity theories. And the point is that for a certain smart set of shifts, these boundary terms vanish. Okay? Yeah? Sorry, which? What's what? Yeah. Are you asking whether these are related? No. The reason why they're not related is that there's a chirality, which is that I picked Q to be lambda 1, lambda 2 tilde, and not lambda 2, lambda 1 tilde. So it was built into, in spinor helicity, you can see it very simply. If I use Q's, it would have to do with like kind of where a certain set of I's are. But there's an alignment. So that's a great question. You could ask, wait, what about parity? Why are these in different categories, right? It's because you have to make sure that the shift you do is aligned with the plus and minus in the right way. In fact, if you study these conditions, you'll realize Q is nothing other than a polarization tensor. It's the definition of a polarization tensor. So you have to choose which polarization you have. And this statement is just saying that you have to choose it aptly and correctly aligned with what the helicities are for the legs. Okay. Now let me just say in words where this goes. So this was for the simplest case of a 2-line shift. At this point, people have studied 3-line, all-line, everything in between. Let me just mention the theories which you can now construct this way. So you can define on-shell constructible theory as a theory in which every amplitude can be recursed down because there's a good shift for it, down to some finite set of inputs, which are like the 3-point amplitudes. And at this point, we can do this for all gauge and gravity theories with any matter content, all renormalizable field theories in 4 dimensions, including QCD, electroweak Higgs, all that stuff. So it's extremely powerful in general. Okay. Any questions about that? OK. Maybe if you bear with me, let me mention the last part of the story, which is a class of theories that I have yet to say any words about, really, which is effective field theories. Okay. Now, and it's going to connect to this recursion directly. Okay. So this whole story was in its infancy created for gauge and gravity theories, and those are, of course, great, beautiful theories. You can add supersymmetry, add what you like. Everything works out nice. But of course, there's a huge class of theories that we even have phenomenological interest in, which are effective field theories. And you could ask, how powerful is this if I can't say anything about those? Right, these aren't UV complete theories. They have bad UV behavior. OK, you say, there's no way this can describe that. But then I say to you, wait a minute, gravity has all those bad properties. Gravity is non-renormalizable. At large momentum, it famously is supposed to have amplitudes that blow up, except we found a certain set of shifts where it actually goes to 0. Okay? Despite all those terrible properties, we can construct all the graviton amplitudes. Okay? So clearly, renormalizability, all these things we're used to thinking of as the death knell for a theory, are actually irrelevant, because this all applied to gravity just wholesale. Okay? So there's in principle nothing wrong with saying, let me apply recursion relations to pions, say. Okay? But let's say you did that. Let's say you just did this construction. You computed the boundary term and asked, well, what can I do to make B infinity go to 0? You'll find that there's nothing you can do. The reason is actually pretty simple. There's no helicity you can exploit. When I say minus and plus, I'm talking about scalars. There's no freedom. Okay? So if you just apply these Bcfw recursion relations as stated to EFTs, it just wouldn't work because this B infinity would be present. Okay? But this actually connects to a physics point, which is that with one extra ingredient, you can actually define all amplitudes in EFT. Okay, so let me tell you what that ingredient is. Thus far, keep in mind, what have we used? Lorentz invariance, little group, dimensional analysis, and factorization. For EFTs, I want to add one more element. Okay? So in particular, if I told you I was going to construct an EFT without a Lagrangian, you'd say I was crazy, because we know how to construct EFT Lagrangians. You apply CCWZ to G mod H. You do all that fun stuff, write down pion action. But I'm not allowed any of that. I can't write down a Lagrangian. I refuse to. It's too gaugy. So instead, I'm going to just write down the answer. But how do I do that without saying anything but something about the amplitude? Well, it turns out the key extra ingredient is something that Nima discussed for the case of gauge theories and gravity theories, which is the soft limit. Okay. So let's consider an extra constraint. Okay. So this is an addition. This is the fourth thing you can add. But we'll see that this really minor ingredient can let us construct all the EFTs that we care about. And what do I mean by the soft limit? Let me just define it quickly from what Neiman said. It says take an amplitude, which depends on some momentum, some external leg p, and take p goes to 0 and ask how quickly it vanishes. Okay, for the case of gauge theories and gravity theories, we saw it doesn't vanish. There's a pole. Okay, so this if you like, this sigma is a -1 because there's a singularity, which, as we saw, corresponds to long-distance Coulombic and gravitational forces. Okay, so that's a real physical meaning to that. But when sigma is positive, it just means that the amplitude vanishes. Okay, so this is a well-known fact, actually, about the pion Lagrangian that may have been alluded to when Csaba spoke. But if you take the pion Lagrangian, okay, schematically, the nonlinear sigma model. Lagrangian, right? So I'm adding, with various normalizations. It's, of course, a two-derivative theory. Right? Every interaction has two derivatives, right? Because there's just two partials there. So naively, you'd think, well, if I look at a 10-point amplitude and I take a soft limit of an external leg, then surely that can't vanish because there's not enough derivatives. Okay? But the magic of the so-called Adler zero is that these pion amplitudes actually vanish in this limit. When sigma is actually 1 for these chiral Lagrangian amplitudes. Okay, so it's a well-known story, and it's even understood by Susskind and Frey that you could actually construct the theory from this condition rather than thinking of it as a byproduct of the Lagrangian. Okay?
So somebody can just say that sigma has to be bigger than 0?
Yes, a vanishing soft limit. So this is the definition of a soft limit, but the statement that sigma is greater than 0 is the statement that it vanishes. Okay? Now let me quickly just show you a toy case and then tell you how powerful this is in an example that I find very cute, which is, let's just take a Nambu-Goldstone boson Lagrangian of a single flavor. So this is just some function of k d phi. So you get like k inflation or something. OK, so this is just some summation of terms that I'll call lambda 2n d phi to the 2n summed on n. Okay, which I'll canonically normalize the first term, but then everything else will just be free parameters. d phi to the 4th, and the 6th, d phi to the 6th, etc. Okay, infinite series. Okay. Now this is like an even stupider version of this type of zero, because it's obvious that if you compute an amplitude, every external leg comes with a derivative. It's derivatively coupled, okay, manifestly. So without even doing a calculation, you know that when the soft limit is taken, then this should go as p to the 1. Okay, take any external leg, take it soft. There's one derivative per field, so sigma should equal 1. Okay, that's fine, all good. This is we've really learned nothing. Everything was entirely obvious from the shift symmetry. But let's see a case where you can learn kind of a little bit more. Okay, in particular, let's take this theory structure, which is one derivative per field. And rather than demand that sigma equals 1, let's demand that it's 1 power higher. Okay? So we'll take the same ansatz, and let's just ask that the amplitude vanishes with 2 powers. Okay? So a when p goes to 0 equals p squared. Okay, so what that means is all the terms that vanished only linearly in p have coefficients in front of them. Those coefficients depend on these lambda 2n's, and I just want to solve those set of equations and see what I get. What happens? Well, you can just do this order by order, and you'll get a Lagrangian where those lambdas are actually constrained. So what's the Lagrangian? Let me write down a couple terms. So really, it's at the level where there's a kinetic term, it's a quartic term. But then when I start going to higher point, I realize that the higher order terms depend on the lower terms. Why do I say that? Well, for this soft limit to exist, it defines a relation among the couplings. And I'm just solving for what that set of relations are. And you'll find that this is actually 4 times lambda 4 squared d phi to the 4 plus 20 lambda 4 cubed d phi to the 6th. And at each order where you have a free parameter, you can fix it with the soft limit of the next lower point amplitude. It goes on forever. You can do this. But if you're a little bit clever, you'll recognize that this is actually the Taylor expansion of a known theory, which, again, has a name. This is the Taylor expansion in some funny units of the square root of 1 minus 8 lambda 4 d phi squared, which is known as the Dirac-Born-Infeld action, DBI action. which arises in a very interesting physical context. Okay, so this action actually describes the motion of a brane in 5 dimensions. The way to see that quickly is that this root, square root of junk, is actually just root of det g. Okay, det g depends on a coordinate phi, which labels the position of a brane in 5 dimensions. Okay, so it's a 5D flat theory. Shifts of phi, which are the Goldstone boson translations, are just shifts of the brane. That's an isometry. But this thing has more symmetries than that original action. Okay. The reason why it has more symmetries is that if you talk about a brane in 5D, it also has boosts, rotations, and so on. And those are also non-linearly realized in this formula, but in a much more complicated way. Okay, so this is precisely what I mean by symmetries being an output of the soft limit. I assume sigma equals 2 as an input, an extra input that constrains my S matrix. And then, as a consequence, we can derive what the theory is. Okay?
So are you including soft limit for any number of external legs?
Yeah, the soft limit for one external leg, but for any amplitude.
Oh, I see.
So it's a single soft limit for all amplitudes, indeed.
If you impose all the legs, then you'll be too strong.
That's actually a different condition. So you could ask about double soft limits, even before doing all of them. Just double soft limits, triple soft limits. Well, let me mention one thing that's interesting about the double soft limit, which relates to the pions, which I didn't consider here. But you could ask, what about the higher order poles, higher order soft limits? Well, you could ask, if you're talking about the pion Lagrangian, what's G mod H? You said you wouldn't say symmetry, but the S matrix should tell you what the symmetry is. Well, the double soft limit, the commutator of the double soft limit, actually extracts the algebra of the G mod H group. Okay. So I think I'm probably running out of time, but let me just finish by saying the following. Really just last statement, which is that you can use this formalism to construct dBi. If you apply the exact same logic, you can build actually a whole slew of effective field theories that have names. Let me just summarize them here. Which is, sigma equals 1 is the pion Lagrangian, the nonlinear sigma model. Sigma equals 2 is the Dirac-Born-Infeld action. And another theory which has shown up in the literature known as the Galileon, which actually is just a scalar field theory that happens to describe the longitudinal mode of a massive graviton. And you can even go up as far as sigma equals 3 to get something now known as the special Galileon, which is a subset of this, which is an enhanced soft limit. And I mention this because, well, much like in the first lecture, obviously using this construction, I can build a full S matrix. You can just do that. But we can also automate it. So I won't go through the details of that. But at this point, we also have just on-shell recursion relations, which take these as inputs, just the sigmas, and then build the full S matrices for all these theories, because they're actually they have this nice long distance property. Okay, so that's it for today. Next lecture, I will discuss the sorcery that you would never be able to see in a QFT formalism that has become evident in the last 10 years or so. Thank you. Hey, yeah.
Yeah. So in order to construct all amplitude,
Yeah.
then how do you determine B?
Great question. Okay, so let me show you the trick. So I wanted to cover this, but I didn't have time.
Still at my
Oh, yeah.